Testing 1, 2, 3. Testing 1, 2, 3. Testing 1, 2, 3. All right, let's get started. Okay, so where we left off was looking at divide and conquer algorithms. Remember, the idea of a divide and conquer algorithm was to first break your problem into smaller subproblems, then solve those problems recursively, and then combine or conquer those recursive answers that you got into an answer to the final subproblem. The first example we saw was this multiplication algorithm here. So we solved 3 subproblems. These are the 3 recursive calls. And each of those were smaller subproblems. They had, instead of n bit numbers, they took n over 2 bit numbers. Okay. And then, so that was the divide step. And then the conquer step was this part to combine those recursive results, those P1, P2, P3, combine them into an answer for the final, for the original problem. We then started on another algorithm. That's the divide and conquer algorithm. And this was the merge sort algorithm. Merge sort is a sorting algorithm. So the input is an array of n numbers, and you want to output the array in a sorted order. Okay. The idea is if you have your input, we divide it into two parts. Okay, and we sort recursively, make a recursive call to merge sort each of the parts separately. So in this case, when we sort this guy, we get 2, 3, 5, 10. And when we sort the right half, we get 1, 6, 7, 13. All right. Now, yeah, so where do we go from here? The next step is like, how do you combine these two merge subpaths into one merge list? Of course, you could just sort everything, but that defeats the purpose of only making recursive calls to smaller functions. So you also have this fact that you're almost like you got the two halves sorted, so you can use that. So let's see, how do we merge? So here they are: 2, 3, 5, 10, and 1, 6, 7, 13. So what's the first element in the merge list? If we were to merge these into an output, the first element would be 1, right? This is the output. The first element would be 1. But okay, how do we find this one? How do we find given these two lists, how do we very simple way find the smallest element? We just, like, it's either this or this. So we just compare these two guys to take the smallest one, right? That in the sorted output, the first element has to be either this one or this one. It cannot be something else. It cannot be it cannot be like here or something like that. Right? So we can put that. Now, for the rest, we can make a recursive call to merge from this list and from this list. Right, so it's a very simple way to think about merge. We find the smallest element, and then we remove that element from the array it came from, and we make a recursive call. Okay. So let me write this down. So merge. We'll take two arrays, the first and the second. The first one of length k and the second one of length L. Okay. If x1 is less than or equal to y1, so if the top if x contains the smallest element, then we return x1 concatenated with, so this all dot means concatenation. I'll put it here, concatenation of lists. Okay, and then the recursive call to x. Now we don't want the first element. We don't want to pass the first element anymore. We want to cut it from the list. x2 to k and y 1 to L. Let's see. Else, otherwise, we do the same thing, but the role of X and Y is reversed. Else, return Y1 concatenated with merge X. We give the full X now, 1 through K. And for Y, we start at 2 because we used up the first element here. The only thing missing in this code is the base cases. So the base case is if one of the arrays becomes empty. So let's say 6, 7, 9, and here you've got 1, 2, 3. Let's say these are your two arrays. Well, so first you make this call. Then you make the call, you get rid of the 1. So you 6, 7, 9, 2, 3. Then you get rid of the 2 because 2 is smaller than 6. 6, 7, 9, 3. And finally, you get rid of the 3. So you have 6, 7, 9, and an empty array. And at this point, now you say, okay, I don't have anything else in X. All my elements are now in Y, and they're sorted. So in that case, I just return Y. So if, let's put in here, if K is equal to 0, which is our way to indicate that the X array is empty, then return Y. And the same with the roles of X and Y reversed. If L is 0, then return X. All right, so let's see. On this one, let's see what happens. We put 1 and we make a recursive call as I've drawn. Then we compare 2 and 6. And so 2 is smaller. And then, oops, so 2 is smaller. That means that we put it in our output and reduce the X list. Next, we compare 3 and 6. And for that, the smallest is 3. So we remove it from our list. Next, we compare 5 and 6. The smallest is 5. We remove it from our list. And we compare 6 and 10. Now here, the smallest is 6. Remove it from our list. We're left with 7 and 13. Compare 7 to 10. 7 is the smallest. So we then compare 13 to 10, and 10 is the smallest. And then we have our base case, only Y is left, and we output 13. All right. Any questions about the merge routine? Yeah.
So I just like a little bit confused with when it comes to like when we program this, right? We usually say like index 0. So like if we want to write it on homework, not that we want to say 1 or 0.
So yeah, the question is, we were starting the indices from 1 rather than 0. I think, in programming, when you're programming, you're often starting, in most languages, you're starting indices from 0. In here, I think I'm following the book or other lecture notes, they're starting from 1. It doesn't matter if, in homeworks or exams, you think this is ambiguous, you can always just state explicitly, I'm assuming that array starts from 0 or from 1. Okay, so the running time, what's the running time of this merge routine? It's a recursive algorithm, right? And it's a tail recursive, meaning that it does some work and then calls a recursive function, and that's it. There's nothing more, and then it stops. It doesn't need to do anything after the recursive call is done. So the non-recursive work, well, it's it's basically constant work, okay? Because if you implement this correctly, you just pass along your input. You don't have to actually copy it. You pass along X, like a pointer to X or something. And this is constant comparison. And this concatenation is also constant time because you're doing it with just one element. So non-recursive work is theta 1, is constant time. Now here, it's a little simpler to analyze the recursion than we've seen in other cases. In other cases, we've seen this like branching of a tree, like there's 2 or 3 recursive calls, and then we have to count everything. Well, here we don't have to do that because here there's only one recursive call. Right? You're either going to call this guy or this guy. You're not going to call both. So we can just count. Oh, and sorry, and then the non-recursive work doesn't actually depend on the size of the call. So we just need to count the number of recursive calls. Okay, there's a neat argument here that you can make. Initially, number of elements in the input is k plus L. What happens to the number of elements in our recursive call? We're losing exactly one element. In both calls, we're losing exactly one element. So each new recursive call decreases number of elements by 1. Then we stop in the worst case when the number of elements is 1. Right? So I think that's what happened in this example. We stop when the number of elements is 1. We could have gotten lucky, like here, we'll stop when the number of elements is 3. But in the worst case, we can go all the way down to 1. Okay, so we start with k plus L. Each call would decrease by 1. When we get to 1, we stop. So how many recursive calls are there? Is it k plus L? Yep. Why? Because that's how many elements we have. So we start with k plus, so there's 10 apples, each person walks in a room and takes an apple. When there are no more apples, or there's one apple left, no more people are allowed in the room. How many people walked in to take an apple? 10. So it's the same idea here. Number of calls is at most K plus L, which is O of N. Right here, and N in this case is number of elements. It's K plus L. Okay, so total time is order N for merge. Right, we have O of N recursive calls, and each one does constant work. So that's O of N times, let me make it specifically, O of N times theta 1, right, this constant time from here, which is by multiplication property, O of N time for merge. Okay, now this was just a part of the bigger divide and conquer algorithm. This was just the conquer step. So let's try to now write down the full merge sort algorithm. Takes an array A, base case of n equals 1, return A. One element is always sorted by definition. Then we sort the left half, so we call merge sort recursively on A from 1 to n over 2. We do the same thing for right half. N over 2 plus 1 all the way to n. And now we return the merge of those two. Yeah.
Instead of saying the floor of n over 2 plus 1 for the like, would we be able to say the ceiling of n over 2 and not top of the plus 1?
No. Think about it. Ask me after class if you're. I see where you're coming from, but no. Okay. Think if n is a multiple of 2. Then it's the same number. Okay. So that's it. That's the merge sort algorithm. And now we can write down the runtime of merge sort. This is for merge sort runtime. Okay, we have 2 recursive calls, each one of size n over 2. And the conquer step, how long does it take? Well, we just analyzed that. That's O of n. Well, wouldn't it be nice if there was a technique we could use to solve this recurrence relation? Oh, wait, there is. We learned it. It's called Master's theorem. So, Master's theorem. This is, if you remember, this is A, this is B, and D here is the degree of the polynomial, so 1. Okay. You have A equals to 2, B equals to 2, and D equals to 1. And now remember, we're going to check log of base B of A equals to log base 2 of 2, which is 1, which is equal to D. This is case 2. Let me show you guys case 2. Yeah, this was case 2. Those guys are equal to each other. And then the recurrence is n to the power of D times log n. And D in our case is 1. That is n log n. Which is the runtime of merge sort. Right, any questions on merge sort? Yeah. So the question is, what is the time complexity of concatenation if it wasn't, like here I said, it's just one element. What if it wasn't just one element? Well, it really depends on how you implement that. So if these are linked lists, you guys have had linked lists in other classes, yeah. So if I want to connect two linked lists, concatenate them together, I just have to change the end pointer of one list to point to the beginning of the next list. So that's constant time. If I implemented this like if it's two arrays, then I might have to copy all the elements from the second array into the first array, and then that's linear time, because then I have to copy all the elements. Yeah. For homeworks, usually we try to avoid ambiguous situations like this in homeworks, but if there's ever a case where you feel like this should be done, this can be done in constant time, but you're not 100% sure, you can put specifically say, well, I assume that in implementation I can do this in constant time. As a general rule, if you're not sure, state your assumption, either homework or exam. That will really help the graders. Other questions? Yeah. Other questions? To merge sort going once. Oh, question. Huh? How much work you have to show for using? No. I think if you just, you can say, for example, if you write, you have to write down the recurrence relation, and then usually it's okay to give the answer. It's okay to just to give T of n is n log n by master theorem. Now, if you want to say a little more, you can say, yeah, we used case 2. You don't have to show all these steps. You can do that on the side. Yeah. Well, I think in your homework you didn't have big O. In this case, we have big O. Oh, you mean here? Oh, that would be a wrong answer. Good catch. It does matter whether you have a big O. Yeah. Yeah, good catch. Yeah. The difference between T notation and asymptotic notation? Okay, so T of n is, we introduced this, it's just a function that represents the number of steps your algorithm takes. So different algorithm will write down T of n is, and give a formula. So T of n is just, it's literally the number of steps that your algorithm takes. Big O is something different. Big O and big theta, these are not functions. These are categories. So n log n. So when we say T of n is big O of n log n, we're saying that the number of steps taken by the algorithm is at most asymptotically proportional to n log n. That the second part, that's what big O is. It says that asymptotically it is at most n log n. Yeah. So the question is, like, I guess I'll restate it, is here we did left side and right side. Is that the best way to do it? Are there other ways to split? It really depends on your problem. So for merge sort, this makes sense. It gives us this running time. This is a good running time. We'll see in a bit. For multiplication, remember, we had to split it in order to get something faster. We had to split it into, I guess we also split it into halves. We'll see in the next problem that we'll look at that sometimes we don't split it into halves. Yeah. You said again? Yeah, you should, like, that's probably the first idea you want to try when you're solving, trying to come up with a divide and conquer algorithm, is see, okay, does it make sense to split the problem in half? Okay, other questions? Yeah. If I understood your question, what if T of n equal to was 2T n over 2 plus n log n, O of log n. Well, in here, the master theorem, like, doesn't, you can't use it just by plugging things in, because this is not a polynomial. So here, this is similar to one of your homework problems. You can say, look, T of n, so this O of log n, on one hand, it's less than n. On the other hand, it's more than 1. So you could say so T of n is sandwiched between 2T of n over 2 plus O of n, or here 2 of T n over 2 plus O of 1. Right. And now you can solve this with master theorem. And this you can solve with master theorem. Yeah. Now, if they both give like n log n, great. That means you have a solution, but there may be a gap. Right? In that case, you still don't have an exact answer. This is just a aside, not going to be not part of the regular lectures. All right. So what do we gave an algorithm, we proved its running time. What was the next thing? Yeah. Can we do better? So can we do better than n log n? And this is one of the like rare cases in computer science where we sometimes can say, subject to some conditions, no, you cannot do better. And we'll see an example we'll see the proof of why. So this is called lower bound on sorting. I want to pull up a figure for you guys. Right. Okay. So you guys should see that. Okay, so we're going to look at all sorting algorithms that you could possibly come up with that are based on doing comparisons. So I'm going to explain what I mean there. So all comparison based sorting algorithms. Okay, so merge sort was a comparison based algorithm, which means that what it did was compare two elements or compare any elements, and based on that, decide what to do. If you think of other, what other sorting algorithms have you guys seen? You guys seen insertion sort? Yes, you've seen insertion sort. That's also an algorithm that's a comparison-based algorithm because it compares elements. One is bigger than another. Do one thing, something else is bigger than something else, do another thing. Okay, so we're going to be limited to these types of algorithms. So for these types of algorithms, we can show that you need at least n log n comparisons. So here's how we are going to prove it. We can view an algorithm, a sorting algorithm. Let's be specific. A comparison-based sorting algorithm as a tree. Okay, so it is a decision tree. Let me be specific. As a decision tree. All right, so what do I mean there? Consider an algorithm that sorts three elements, A1, A2, A3. Okay. So an algorithm could look like this tree. So what does it mean? We first comparison we do is A1 less than A2. If it's not, then we go recurse down here. If it is, then we recurse down here. So let's say that A2 is bigger than A1. Okay, and then we recurse to the right. And we ask, is A2 less than A3? Right. And if yes, then we recurse to the right. And now that A1 is less than A2 less than A3, I know the order of the elements in the output. It's A1, A2, A3. We don't have to change the order at all. What if we did something else in this algorithm? So what if the answers were different? So let's say that A is equal to 15, 10, and 5. Well, is A1 less than A2? No. So we go here. Is A1 less than A3? No. So we go to the left. This is no, this is yes. Left is no, right is yes. Okay, so we go to the left. We at this point know that A1 is less than A2. We know that A1 is not less than A2, and A1 is not less than A3. So A1 is going to be the biggest element, but we still don't know between A2 and A3, we still have to decide. So we compare them. The answer is no there. So A2 is less than A3, then our output has to be, so what was it? A3 here was the, A1 was the biggest one. And then we were deciding between A2 and A3, and A2 was bigger than A3. So the output should look like this. A3, A2, A1. And in this example, this 15, 10, 5, it's exactly what would happen. So 15 is less than 10. 15 is not less than 10. 15 is not less than 5. 10 is not less than 5. So the output should be A3, A2, A1, or 5, 10, 15. Right. So this tree is a particular algorithm just written in a very specific way and written in a very inefficient way, right? If n was 1,000, this really kind of going to be a huge tree. We prefer to write our algorithm in this kind of pseudocode, which also captures the intuition about why the algorithm is doing what it's doing. But merge sort as well can be on a specific n, can also be just written down as this very big decision tree. Okay, now do you guys see how we can view an algorithm as a decision tree? How many are comfortable with that? Okay, good. Now, what can we say about this tree? So the leaves is a possible output. The number of possible outputs is what are the number of possible outputs for sorting and elements? Here we have 3, 2, 1, 2, 3, 1, 2, 1, 3, 3, 1, 2, 1, 3, 2, 1, 2, 3. Yeah. 2 of n, not quite. Others? N factorial, others? N factorial? It's n factorial, okay. N factorial, why? Because, okay, you have to choose what's going to be the smallest element. It can be one of any of the n elements could be the smallest element. Then we choose what's the second smallest element. So any of the n-1 remaining elements could be the smallest element. And so on. Okay. Like one of the definitions of n factorial is actually the number of permutations of n elements. Okay, so number of possible outputs is n factorial. Now, what about number of leaves? Well, it's also it also has to be n factorial. Because if one of the possible permutations is missing from the output, then the algorithm will not be correct on some kind of input. For example, if like let's say that this guy was not there. This leaf, let's say, was not there. Then on input that looks like this, the output, the algorithm would not be correct because it needs a 3-2-1 somewhere to be able to properly output this. All right, so we know the number of leaves. Now, what about the depth? So depth D, we'll call it D, with D equals 0 being just the root. Okay, so the max depth max depth in this tree has a very special meaning. So the number of comparisons that you make on one of these trips down is the depth that you traverse. Right, so here you do 1 comparison, 2 comparison, 3 comparison, 4 comparison. Right. If you go down this route, then you do only 1 comparison, 2 comparison. The worst case number of comparisons is if you traverse down the max depth path. So this is worst case number of comparisons. Okay, this is I should have said D is the max depth. Max depth D. All right, so we're gonna try to argue about this max depth D and say that it's at least n log n. Yeah. Here the max depth is so if I say 0 is the root, so this is 1, 2, 3, it would be 3. Yeah. Okay, and finally, I want to observe that it's a binary tree. Okay, and a binary tree of max depth D has at most how many leads? Just a general property, nothing to do with this specific tree. A binary tree of max D, how many leaves can you fit in there, guys? 2 to the D. Right, so here's depth 2. So, I've got, sorry, this is depth 1. So 2 to the 1 leaves. This is depth 2. 2 squared leaves, and so on. Okay, now we're going to put all these facts together because the number of leaves we argued is n factorial, and it's at most, we also argued 2 to the power of D, where D is this max depth. So what is the max depth? let's take a log of n factorial less than or equal to d. Okay, so d is at least log n factorial. We can write this as omega log n factorial. And I think one of the identities that I gave you a while back is that log n factorial asymptotically behaves like n log n. This is by earlier identity. Okay, so this is actually it. So this, we said that D is number of comparisons in the worst case. So therefore, any comparison based sorting algorithm takes omega. Remember, omega is like at least, but asymptotically, at least omega log n time. And that's, remember merge sort? We proved that it's O of n log n, big O. This is now matching lower bound, not just for merge sort, but for any comparison-based sorting algorithm. Right? So merge sort is optimal in that category of algorithms. Any questions about this proof? Yeah.
There non-comparison based sorting algorithms that are faster.
Are there non-comparison based sorting algorithms that are faster? Yes. In fact, maybe this will be one of your homework problems. If I give you a stack of cash, like I give you, like in the movies, I give you a bag of, but it's not 20s. I didn't get it sorted right. So there's like ones in there, 5s and 20s. And let's say you go to your criminal bank to turn in the cash, but they're very particular. They want you to line up the bills in sorted order. They're kind of quirky. So you have to sort this bag of bills in the sorted order 1, 5, 20. And let's say you've got like, this was a lot. This is like, you got 10,000 of these bills. So what are you going to do? Are you gonna do merge sort? So split the piles. Are you going to do insertion sort and walk around with the bills? What are you guys going to do? I mean, I know you don't have any experience with this kind of enterprise, but just hypothetically, yeah. Okay, exactly. So you have categories. You have a pile of 1s, a pile of 5s, and a pile of 20s or 10s or whatever. And you would just go one by one and put it in the right category. Okay. How long does this algorithm going to take you? N, order n, right? So maybe the cops won't catch you since it's not an n log n. It's order n, right? You go through every element once. And is this a comparison-based sort? No, you're not comparing two bills like, is this one less than 20? Right. Just to prove that point, it could have been not 1, 5, 20. It could have been a bill with a picture of a cat, a picture of a dog, and a picture of a elephant. So you're never comparing elephant versus cat. You're just putting them in buckets. It's like cat bucket. Okay. So that's an example of an algorithm that yeah. Well, it depends on what you mean by categorization problem. But in some sense, yes, I mean, it then isn't sorting the way you're used to, but it is sorting when you have a fixed amount of categories. Yeah. Yeah.
And you gave an example that I can cross one that sums out and the algorithm doesn't work.
Yeah.
Then why did you write that n factorial is less than or equal to the amount of this?
Oh, because the number of leaves is at most 2 to the d. It wasn't, the n factorial is the number of leaves, but in a binary tree, you don't necessarily have a full tree. Like I drew here a full tree, but you can have a binary tree that's not complete. So maybe this guy is missing, for example. So it's not exactly 2 to the d, it's at most 2 to the d. Yeah.
So for the like categorical to be part of that, did you just like sort the category?
Yeah. Yeah. Yeah.
So why the category for like the one? Like you did mention, why is it not a comparison?
Why is it not compared?
It still compares the object as the category, right?
Okay, but okay, good. So I'm still comparing the object, this $5 bill, to the categories. Is it a 5? Is it a 20? That's a good point. Yeah, let me make this quick. So I'm not checking if it's less than, or if it's, I'm just checking if it's equal to or not. That's what I mean here by comparison-based sort, is it's doing not just, you can always do equality. So the yeah, that. Other questions? Yeah.
What if we put two values in the comparison? What if we have two different lists or like the values that's
Yeah, so what if the values are equal, like here? Well, like what if A1 is equal to A2 equal to A3? So then we would go no, because nothing is less than, everything is equal. And here would go no, and here would go no, and we would output 3, 2, 1. 3, 2, since all the values are equal, this is a perfectly valid output. Yeah. What was it? Oh, which step are you asking about? Oh, because I want to solve for D. So if I have 2 to the D and I want to solve for D, I take a log, and that gets rid of, that brings the D down. And then this I do on the other side to balance. I put a log here and log here. Right. Okay, let's move on to a problem called median finding. This is chapter 2.4 in your book. So you're given a list of numbers S, and you're looking for the median. Remember, the median is the element so that half of the list is smaller and half of the list is bigger. We'll put it formally like this: we take S over 2, and we'll put a ceiling on it in case S is odd. And we want this smallest element. This is like the 10th smallest element or the 5th smallest element of S. So let's do an example. So let's say I've got 2, 36, 5, 21, 8, 13, 11, 20, 5, 4, 1. If I sort S, that's one easy way to solve this problem. So if I sort S, I get 1, 2, 4, 5. I have 2 5s. What's next? 8, 11, 13, 20, 21, 36. Did I forget anything? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I didn't. Okay, so there are 11 elements here. N is 11. S, so S, this is N, is 11. So S over 2 ceiling is 6. And so we want the 6th smallest element for the median. This is the 1st, 2nd, 3rd, 4th, 5th, 6th. This is the median here. Okay. So how do we solve this problem? Well, what I did was one solution, so easy solution. Via sorting, the sort takes n log n time. And then you just, if it's an array, you just go to the middle element. So that's constant time to return the median. But this is, it turns out we can do faster. So it turns out we can have a linear time algorithm for median finding. And that's the divide and conquer algorithm that we'll come up with together in class. Okay, before tackling that, let's make this a little more general problem. Sometimes making the problem more general helps us solve it. We saw this in induction. Sometimes, or in loop invariant also, sometimes having a loop invariant say a little more than what you need for the termination condition is necessary. Like we had, what was the example we did in class in the loop invariant? The multiplication. So we had both Z and M as part of the loop invariant. For the termination, we only needed Z, but to make things work, we needed to do both Z and M. So it's the same here. We're going to have a little more general problem than what we just need for the median. And this is called the selection problem. Okay. Here, the output, the input is S and K, some number K between 1 and the size of S, and the output is the kth smallest element of S. Okay. So in particular, median of S will be selection of S and that S over 2 ceiling. Okay, so well, we want to be able to actually pick not just the middle element, but like the 2nd element or the 9th element or whatever element we want. Okay, so let's try to do this with a divide and conquer approach. The basic idea is that we want to partition the input around some element. Okay, so we want to partition input around some element V, and we'll talk about how to select that element. And then we have SL, SV, and SR. So all SL is all elements of S less than V. All SV is all elements of S equal to V. So there may be many, there may be like 5 of them, and they're all going here. And SR is all elements of S greater than V. So for example, if we can, let's say V equals 5. Here's our array again. Okay, so let's say V equals 5. So now there's something called SV, SL, and SR. So to partition, once we pick 5, we can do this now in linear time, and we just go scan through L, and we put everything according to how it compares to 5. So 2 is less than 5, 36 is more than 5, 5 is equal to 5, then I got 21, 8, 13, 11, 20, 5, 4, and 1. Okay, so I've got these 3 partitions. Okay, so how does this help? Let's remember how many elements are in each. So here there's 4 elements. Here there is 5 elements. And here there's 3 elements. So what if I ask you, what if the question was the 6th smallest element? Looking at this, how do you know the answer? Yeah. 8 is more than 5? Oh, that's a good point. So let's put this here, 4, 1, and 8 will go in this bucket here. So went right before 21. So 36, 5, good. Thanks for the catch. 21, 8, 13, 11, 20. So this is now 6 elements. And this is now only 3 elements. Okay, so now if I ask you, yeah, another mistake. Unless I made another mistake, there are 3 elements in here. Oh boy. You guys are a tough crowd. Okay, 2 elements. 2 elements, all right. Okay, so okay, let's try again. If I ask you for the 4th smallest element, how would you quickly tell me the answer? Anybody, any new hands? Yeah.
So first through SL, there, and then move on to S.
So if I ask you for the 4th smallest element, do you need to traverse through SL, or could you just ignore it? Because you know that SL has 3 elements, and these are the 3 smallest elements. So if I'm looking for the 4th smallest element, I can just ignore SL, and I can say, well, if the 3 smallest elements are in SL, and I'm looking for the 4th smallest element, then I'll be the 1st element in the SV bucket. So similar logic, what if I'm looking for the 11th smallest element, what could I do? Yeah.
11 elements. 11 elements.
If there are only 11 elements in an array, so you just go to the last one. That's correct. That's let's do something harder. What about the 8th element in the array? Yeah. I do not want to sort SR. I do not want to, I want to avoid sorting. Yeah, 8th element, yeah. Yeah, so let me repeat. So if you just want to know which category it's in, then you know that the size of SL plus the size of SV is 5. So if you're looking for the 8th smallest element, you're going to be in SR. You can be more specific because you know 5 elements are in here. So the 8th element, smallest element in total, is the 8 minus 5, the 3rd smallest element in SR. All right, so I can now make a recursive call to SR to say I'm looking for the 3rd smallest element. Okay, that's the intuition of why this partitioning helps. This is the divide. This is part of the divide step. So if I get, let's do, if k equals 2, I can make a recursive call to select. So let's say, yeah, select. That's one. Select S2 is equal to select SL2. Because 2 is less than the 3 elements we have in SL. Select S of 4, as we talked about, is select in the middle 4 minus 3, 1. So this 3 is the size of SL. If I do select S8, this is equal to select SR 8 minus 3 minus 2. So just get the smaller elements out of the way. Right. That's not the algorithm, that's just the intuition of how you could use this partitioning to recurse. But we can actually write down, let's write this down a little more formally. So selection SK is equal to, so in one case, so there's going to be 3 cases. Okay. In the first case, it's when k is less than or equal to the size of the left guy. And in that case, you just go to the left guy and you pass k. If k is more than the size of the left guy and less than or equal to the size of the left plus the size of the middle, then it falls in that middle bucket. And in that middle bucket, we don't even have to make a recursive call because everything in that middle bucket is V, is our pivot element. So we know what it is. It's always V. And the final case is if K is bigger than that. So it's bigger than SL plus size of SV. And in that case, we go right and we pass K minus, let me make some room here, minus SL minus SR. So once we pick the pivot and done the split, this is going to be the rule for the recursion. What we're going to talk about next time is how do we pick the pivot. Okay. That's it for today.
For example, you have 2 5s, like, for example, right here. Oh, can I make it example?
Yeah,
So there, for example, there's 2 5 right here.
Yeah.
If I want to print out the